Lagrange multipliers. Suppose we wish to optimize a function z equals f of xy, subject to the constraint g of xy is equal to k. This means that x and y must satisfy g of xy equals k, and we're trying to find the maximum or minimum value of z, where z is a function of x and y, but also subject to this constraint. G of xy equals k is a curve in R2, and we'll suppose that this is the curve here. And then for the function f, we are looking at level curves of that function f. Now the domain of f, of course, is R2, and then the value z is obtained by plugging in the points in R2 into the function f. What I want you to notice is that if you consider all the points of intersection between the constraint g of xy equals k and the level curves of f here, you should notice that the maximum value occurs here at this point. And what's special about this point of intersection over the other points of intersection is that at this point of intersection, the tangent line to the level curve and the tangent line to the constraint are the same. So if we draw that tangent line, you can see that that tangent line is tangent to both of those curves. Now, what did I do here? What is this perpendicular line here? Well, we know that the gradient of the function f has to be perpendicular to this tangent line, but also the gradient of the function g must be perpendicular to that tangent line. Now, to be fair, we don't know which direction the gradient points, but we do know that it must be perpendicular to the tangent line. Therefore, the gradient for the function f and the gradient for the function g are some kind of a scalar multiple of each other. That is, we can say the gradient of the function f is equal to some multiple of the gradient of the function g. And this number here we call lambda, and it is some constant. And this number lambda is what we call the Lagrange multiplier. And we can use this Lagrange multiplier to help us find the point at which the function f has a maximum or a minimum value when subject to a particular constraint. So the method of Lagrange multipliers is used to find the maximum and minimum values of some function f. Now, the function f could be a function of 2 or 3 variables. It could actually be a function of n variables. But if we have a function subject to that constraint, assuming that the gradient of g is not 0 on the surface of g, we can find all values of x, y, and z and lambda such that the gradient of f is equal to lambda times the gradient of g, and the function g must also be equal to k. Once we do that, we simply evaluate at all the points x, y, z from what we get up here, and the largest of these values is the maximum and the smallest is the minimum. Notice that if we write the vector equation, gradient f equals lambda times gradient g, in terms of its components, then we get the following equations. Fx equals lambda times gx, fy equals lambda times gy, and fz equals lambda times gz, and also g of xyz must be equal to k. And for functions of 2 variables, it's a similar thing, except now, of course, we only have to look at the partial derivatives of x and y, or with respect to x and y, because there's only 2 independent variables. So let's consider the following example. We want to find the extreme values of the function f of xy equals x squared plus 2y squared, which I have a graph of right here, on the circle x squared plus y squared is equal to 1. So this is our constraint. So again, we have f of xy equals x squared plus 2y squared. We can easily calculate the partial derivative of f with respect to x and the partial derivative of f with respect to y. And then we have g of xy must be the function x squared plus y squared, which we also know is equal to 1. But the partial derivative of g with respect to x is 2x, and the partial derivative of g with respect to y is 2y. So now to find the possible values of x and y, where we might have a maximum or a minimum value of f, we need to set fx equal to lambda times gx and fy equal to lambda times gy. And so here, this is going to be 2x is equal to lambda times 2x, or 4y is equal to lambda times 2y. Now, when trying to solve a system of equations like these, don't divide by anything. So what I'm going to do here is write this as 2x minus lambda times 2x is equal to 0, and that is 2x times 1 minus lambda is equal to 0. And then for the second equation, we have 4y minus lambda times 2y is equal to 0. And we can write this as 2y times 2 minus lambda is equal to 0. Now let's just start with the first equation. Here we know that either x is equal to 0 or lambda must be equal to 1. Now, if x is equal to 0, let's think about what that means. We know the constraint must always be true. So keep in mind the constraint here is x squared plus y squared must always be equal to 1, no matter what. So if x is equal to 0, we can plug x equals 0 in here, and we end up getting y must be equal to plus or minus 1. Now let's consider the other part. If lambda is equal to 1, then if we plug that into the second equation here, we get y must be 0. And if y is 0, you can plug y equals 0 into here and get x must be plus or minus 1. So now if we consider all the possibilities here, what we have is x equals 0, y equals 1, x equals 0, y equals negative 1, x equals 1, y equals 0, and x equals negative 1, y equals 0. So we have the 4 points 0, 1, 0, negative 1, 1, 0, and negative 1, 0. And now it is simply a matter of plugging these into the function. So remember, the function f of xy is equal to x squared plus 2y squared. And so f of 0, 1 is going to be 2. F of 0, negative 1 is going to be 2. F of 1, 0 is going to be 1, and f of negative 1, 0 is 1. And so now we can conclude by simple comparison that these are the maximum values of the function f, and these are the minimum values of the function f, subject to those constraints. Now if you go back to the curve here, you can kind of see that on the curve. So you can see that when you plug in x equals 1, y equals 0, you get this value here, and that corresponds to 1 on the z-axis. Also, f of negative 1, 0 corresponds to 1 on the z-axis. And then if you plug in the point x equals 0, y equals 1, which is right here, you can see you get this point, which is z equals 2. And when you plug in x equals 0, y equals negative 1, you also get z equals 2. And here are the level curves of f. So here are the level curves here, and here is the constraint here. And you'll notice that the level curves and the constraint are parallel to each other or tangent to each other, have the same tangent line at those 4 points. So the Lagrange multiplier method is a really keen method for finding maximums and minimums. Now let's revisit a problem that we did in a previous section. We want to find the maximum volume of a box if the surface area is 12 square meters. And remember, the box here has no top. So first, just like before, we can say the volume of the box we know is x times y times z, and the surface area of the box is equal to xy plus 2xz plus 2yz, and we know this must be 12. Now, what we did previously when we solved this problem is we solved this equation for z, and then we plugged it into our volume. We don't need to do that anymore. What we can do here is simply realize we have a function that we're trying to maximize here, subject to the following constraint. And so we just need to take the partial derivatives of each of these functions with respect to x, y, and z, and then set up our Lagrange equations. So we know that Vx is yz, Vy is xz, and Vz is xy. Furthermore, we know Sx is y plus 2z, Sy is x plus 2z, and Sz is 2x plus 2y. So our Lagrange equations are going to be yz is equal to lambda times y plus 2z. Then we'll have xz is equal to lambda times x plus 2z. And finally, xy is equal to lambda times 2x plus 2y. And then don't forget, these also have to satisfy the constraint up here. And I must admit, I'm calling these the Lagrange equation. These are the equations that deal with the Lagrange multiplier. Technically, they're not really called the Lagrange equations. But now let's go ahead and solve these equations. So we have 4 equations, and we have 4 unknowns, right? X, y, z, and lambda. So what values of x, y, and z satisfy all 4 of these equations? When solving these equations, there are no general rules for solving these, but sometimes you got to be a little bit creative. So what I'm going to do here is multiply this first equation by x on both sides, multiply the second equation by y on both sides, and multiply the third equation by z on both sides. And if we do that to those 3 equations, we get the following. And now if I take these 2 equations, I can set the right-hand side of each of those equal to each other because they are both equal to x, y, and z. And generally speaking, lambda is allowed to be 0, but in this case, lambda can't be 0, because if lambda is equal to 0, when we go back up to the original equations here, that would imply that all of these would equal 0, which would imply that all of these would be 0, which would contradict the fact that this has to equal 12. So in this case, we know lambda can't be 0, but if we divide by lambda on both sides, we get xy plus 2xz is equal to xy plus 2yz. And if we subtract xy from both sides and then divide by 2 on both sides, we get xz must be equal to yz, or xz minus yz must be equal to 0, or z times x minus y must be 0. And that means either z is 0 or x is equal to y. And we know that z cannot be 0 because z is one of the measurements of the box. So all of x, y, and z must be greater than 0. But we now know that x must be equal to y. So now let's take the right-hand side here and the right-hand side here and set them equal because we know they are both equal to x, y, and z. So if I do that and ignore the lambda there, we have xy plus 2yz must be equal to 2xz plus 2yz. I can cancel the 2yz on both sides, and now we know xy must be equal to 2xz. But we also know that x is equal to y, or y is equal to x. So I can replace the y here with x, and that gives us x squared equals 2xz, or x squared minus 2xz is equal to 0. And if I factor out an x here, we get x times x minus 2z is equal to 0. Now, we already mentioned that x itself can't be 0, but this could be 0. And so if x minus 2z equals 0, this means that x is equal to 2z, or z is equal to x divided by 2. So the x coordinate is x, the y coordinate is also x because y equals x, and the z coordinate is x divided by 2. And those have to satisfy the original constraint. So if I plug those in up there, I'm going to get x times y, which is x squared, right, because that's x times x, plus 2x times z, z is x over 2, plus 2y times z. Remember, y is x and z is x over 2. This must be 12. And so this is x squared plus x squared plus x squared must be 12, or 3x squared is 12, which means x squared equals 4, which means in this case x must be positive 2. And if x is 2, y is also 2, and z must be 2 divided by 2, which is 1. And so the dimensions that maximize the volume of the box are 2 meters, 2 meters, and 1 meter. And the maximum volume, of course, is xyz, which is 2 times 2 times 1, which is 4 cubic meters. Another example here, let's find the points on the sphere that are closest to and farthest from the point 3, 1, negative 1. So here's what that sphere might look like, and here is the point 3, 1, negative 1. Here. And we want to find the point on the sphere that is closest, and then also there should be a point on the other side of the sphere which is farthest away. So if I have a point x, y, and z on the sphere here, the distance between that point, which is point P, and the point 3, 1, 1 is going to be the square root of x minus 3 squared plus y minus 1 squared plus z plus 1 squared. All right, and we are trying to maximize and minimize d. To do that, we know we just need to maximize and minimize the function on the inside of the radical here. So I'm going to let f of xy equal that function on the inside. So x minus 3 squared plus y minus 1 squared plus z plus 1 squared. And so we're trying to find the extreme values of this function subject to this constraint. So let's go ahead and get our partial derivative. So fx is going to be 2 times x minus 3. Fy will be 2 times y minus 1. And fz is 2 times z plus 1. Now the function g is this function right here. So we have g of xyz is equal to x squared plus y squared plus z squared, and that's equal to 4. Oh, and I messed up here. I should have f of x, y, z. It is a function of 3 variables. There we go. So let's go ahead and find gx. So gx is 2x, gy is 2y, and gz is 2z. And now to solve for x, y, and z that are subject to the constraint, we are going to set 2x minus 6 equal to lambda times 2x, 2y minus 2 equal to lambda times 2y, and 2z plus 2 equal to lambda times 2z. In the first equation, if we solve for lambda, we're going to have 2x minus lambda times 2x is equal to 6. And then we can write 2x times 1 minus lambda is equal to 6, or x is equal to 6 divided by 2 times 1 minus lambda, which is equal to 3 divided by 1 minus lambda. And I misspoke there. We're solving for x, not lambda. And we can similarly solve for y and z in the other two equations here. Okay, and now we know that those have to satisfy the constraint above, which was x squared plus y squared plus z squared has to be equal to 4. So now what I'm going to do is substitute these values for x, y, and z into this equation. And that gives us the following. And now we can solve for lambda by simply multiplying by 1 minus lambda quantity squared on both sides. When you do that here, it's going to cancel out. And we get 11 equals 4 times 1 minus lambda squared. That is 11/4 equals 1 minus lambda squared. Or 1 minus lambda is equal to plus or minus the square root of 11 over 2. Or lambda would be equal to 1 plus or minus the square root of 11 over 2, which is 2 plus or minus radical 11 over 2. And now we simply take these two values for lambda and we plug them back into these equations here to find x, y, and z. So for example, here we know that x is equal to 3 divided by 1 minus lambda. So that's going to be 3 divided by, and then we have to do these one at a time. So the two values for lambda are 2 plus radical 11 over 2 and 2 minus radical 11 over 2. So let's just plug in the first one there. So we have 1 minus 2 plus radical 11 over 2. And then we just change this 1 here to 2 over 2. And that is going to give us 6 divided by 2 minus 2 plus radical 11. And that is 6 divided by negative radical 11, which is negative 6 radical 11 over 11. So that's the value for x with this value of lambda. And then we can solve for y. So y is 1 over 1 minus lambda. This is 1 over 1 minus 2 plus radical 11 over 2. Once again, we will change 1 to 2 over 2. And then we'll multiply the top and bottom by 2 to give us 2 divided by 2 minus 2 plus radical 11. And this is 2 divided by negative radical 11, or negative 2 radical 11 over 11. And similarly for z, z is negative 1 over 1 minus lambda. So z is just the opposite of y, and that means we're going to have 2 radical 11 over 11. And so one of our points is negative 6 radical 11 over 11, negative 2 radical 11 over 11, and positive 2 radical 11 over 11. And then, so that corresponds to this value of lambda here. And then when you plug in this value of lambda, you are going to get 6 radical 11 over 11, 2 radical 11 over 11, and negative 2 radical 11 over 11. And that corresponds to this value of lambda. Now, if you go back to the picture, we can see clearly that this point P has a positive x-coordinate and a positive y-coordinate. And so the point P that is closest must be the point down here that has a positive x and positive y. So this point here is the closest point. And then by process of elimination, we know that this point must be the farthest point away. In the next example, we are once again looking at the function f of xy equals x squared plus 2y squared. But this time it's on the disk. X squared plus y squared is less than or equal to 1. So you can see we have the same boundary as we did in the first example, but now we're also including all the points on the inside. And we know from the sort of extreme value theorem that a maximum and a minimum must exist. And if they do exist, they have to occur at either the boundary or the critical points. Now, we already know from the first example that the only points on the boundary that we need to consider are the points 1, 0, negative 1, 0, 0, 1, and 0, negative 1. Furthermore, for the critical points, we just need to take the partial derivative with respect to x, which is 2x, and set it equal to 0, and the partial derivative with respect to y, which is 4y, and set it equal to 0. And when we do that, we come up with x equals 0 and y equals 0. So the only critical point is the point 0, 0. And then we simply plug all of these values into our function. And we can see that we have a maximum value at the point 0, 1 and also at the point 0, negative 1. And we now have a minimum value at the point 0, 0. The concept of Lagrange multipliers can also be applied to a function that has two constraints. So if f is your function and g and h are your two constraints, we are simply going to solve the equation where the gradient of f is equal to lambda times the gradient of g plus mu times the gradient of h. And that's going to give us the following equations that we have to solve. It's the exact same concept, it's just more complicated because we have more variables and more things to consider. Conceptually, what we're doing is finding the point at which the constraints meet and form two vectors, the gradient g and gradient h, and at that same point, the gradient of f can be expressed as a linear combination of those two vectors. I am not going to do an example with two constraints, but the process and the setup is identical. And that concludes this video lesson.